Now we want to talk about threshold. So we consider like it's random. We learned about this in the undergraduate graph theory course. And yeah, this is an interesting object. You have n vertices and each pair of them you independently random add on x with probability p and you get graph. And then they give you a distribution over if it's labeled vertices labeled. And oftentimes it provides constructions in many interesting institutions. And in undergraduate graph theory, we define something called threshold. Threshold is a function to the monotone property P in PNP. Let's say monotonically is a function like T of x that is defined arrowy. At this GNP almost always do not satisfy Q if this Pn divided by Tn goes to 0. Then this almost always satisfy Q if tends to infinity at that point. Here almost always, or sometimes we say with high probability, means that the probability to satisfy P is here 1 minus 0, 1. As n goes to infinity, the probability tends to 1. And it's almost. And we learned about this in the undergraduate course. For example, I mean, we learned that the threshold for containing subgraph A4 is like some constant type n to the negative 2. So one thing is that this threshold from this definition is not unique. So this is threshold, this is also threshold, this is also threshold, this is also threshold. So you can write any one of them. So this is a threshold. And that's what we learned. And also threshold for the connectivity is like log n over n. And for Hamilton cycle is log n. So those are the things that we. And in general, we are interested in how to compute or how to estimate this threshold. Is there any good way? And let's go back to this example. How have we computed? One easy way is that we consider the expected number of K4s in GNP. How many in expectation are there? There are answers or many choices of the vertices. And then that gives you the 6. The probability that all 6 of them are here is n to the p to the 6. So this is roughly like constant. If p is n to the, there will be 2 over 3. Moreover, and you can say that this is like a zero of 1 if T is 0 and T negative over 3. This is going to infinity if T is much bigger than n to the negative 2 over 3. 0 omega is 0. And from that, what we know? From above, you directly get this is 1, this is 2. From 1 and Markov inequality, you directly get that the probability that and this GNP contains at least one copy of P4 is what? M of 0, 1. If P is 0. So that satisfies the property that the first one. And to check the second one, I mean, you cannot directly get it from this 2. But the 2, together with some technique, some probability technique for the second moment. Again, this is something that we have learned in undergraduate course, practical course. Or you can, I mean, we also learned it in the probability method. But together with that, we show that the probability that G and P contain at least one copy of A4 is at least 1 minus 0 over 1 if P is much bigger than the relative 2. Okay, so this gives us some idea. So maybe computing the expected number of copies here. I mean, if your property is about containing some structure, then computing expectation is very natural. Then they might give you and however, I mean, we have to be a bit more careful. For example, let's consider this graph. So you have K4 together with one vertex. I say this is F0. And what's the expected number of F0 in G and T? You have like n to the 5 vertices, then you have 7 edges. You have this. And this becomes constant. So this is like becomes constant if P is around like n to the minus 5 over 7. N to the minus 5 over 7 is like smaller than this. But what do we know? When P is n to the minus 5 or 7, and even if like you multiply large number here, and still this one is for large n, this one is much smaller than this number. This is 0 of n to the negative third. So this does not contain A4. Hence, no absolute, almost always. With high probability, it does not contain K4. Hence, it also does not contain 0. This is true even if, I mean, this one is bigger. You choose the number between this number and this number. And still, it's fail. So, this shows that this expectation might not be a good idea to actually find the threshold. I mean, this is indeed why this happened. For this, to, I mean, what's the, so if P is this number, then expected number of K4s in GNP is what? You choose 4 vertices and then you like equal to 6, and that's like n to the negative 2 over 7. But if K4 is in G and K with this low probability, and what? Each of these vertex has the with high probability that degree n over n times 2 P. So all of these give us the copy of F0. Then it has what? 4 times NP, roughly that's like 4 times n to the like 2 over 7 copies of F0. So it is very unlikely to have a copy of F0, but once it has many. Because of that, the expectation is actually multiply of this which is constant, while the probability of actually it has 0 is very small. So in order to avoid it, I mean, what you can do is instead of just for given F, instead of just computing the expected number of F in GNP, you consider the all subgraph of, and then you do this computation. In fact, I mean, it is known that the for fixed F for F of cos aside, so like this case of the K4 or the K4 attached with one leaf, that's a fixed graph. On the other hand, the like connectedness or Hamilton cycle is not fixed, then growth is growing. So unlike this case, if you just consider the fixed graph, and this strategy of all considering all subgraph actually like give you what you want. In other words, I mean, what you do is you compute this for all your subgraph, and then you find the p, which makes that all of this expectation is at least some constant, or say 1, and that will give you a threshold. And this motivates the following definition of expectation threshold of a graph f is a, let's try it this way. It is minimum p such that expected number of f prime in G and P is at least 1, say, for all f prime is a subgraph. And it's known that I mean, this actually gives the, I mean, correct threshold for any specific fixed graph. But one of our more general graph, Hamilton cycle, which is a structure which is not like constant size, but it grows with the. And in any case, this actually provides a lower bound. On the threshold. Why? I mean, with this P, I mean, some f prime here, the expectation is 1, right? So due to this definition of the threshold, if your probability is much smaller than the number I just mentioned, and this expectation go to expectation of this specific f prime go to 0, so it's 0, 1, and you apply the Markov inequality to show that with high probability your graph does not contain f prime. Your GMP does not contain f primes, hence it does not contain f. Okay, and let's consider other case. For Hamilton cycle, what's this threshold? expectation ratio. So there are like n factorial way to choose the vertices. Then in order to complete it, you add a edge between them, then you get the Hamilton factor. And there are this is way of finding a sequence. And then each sequence you can consider cyclic orientation or flipping. It's many choices of possible Hamilton factor. And what's the expected number of Cn in GNP, that out of all this, each of them, the probability that it's chosen is p to the n. So you have this, and you want this to be 1. So is some constant type 1 over n. So expectation threshold is 1 over n, but actual threshold is log n over n. We know this. So there are some gaps. It's not like your expectation threshold actually give you the actual threshold, but there could be some gap. And where does this gap come from? One thing, what we did to compute the threshold for Hamilton cycle is that if P is sufficiently smaller than that, then she has an isolated body. Almost sure. Oh, she almost always have a isolated body. So that's what we prove in the undergraduate graph theory. So if you have a vertex with degree less than 2, and obviously you don't have a Hamilton factor. So this is actually, in order to overcome this, it's like a coupon collector time problem. In order to overcome this, your probability has to be bigger than log n over n. And this log n is actually coming from this local obstacle. And in this case, as long as you overcome this local obstacle by multiplying log n, you're okay. You have a Hamilton cycle. So it's showing that this local obstacle is actually the critical. That's the essential one. And if you consider other structure, and then you consider the threshold, and you often see this kind of logarithmic. And indeed, Kahn and Carlyle conjecture that this is not a coincidence. They conjecture that for whatever f you consider, the threshold is at most expectation threshold times log n. And this is called Kahn-Carlyle conjecture, and this is recently resolved. Then we're going to talk about that. Okay. And in fact, everything here can be stated in more general way. So let's, consider the hypergraph, say G sub Hamilton, G hat with the vertex set in all the pairs. So it has n choose too many vertices. And H set being the H set of Hamilton cycle is a Hamilton cycle in your KL. So for example, you have like 1, 2, 3, 4, 5, then your vertex set is 1, 2, 1, 3, 1, 4, 5, 2, 3, 2, 4, 2, 5, 3, 4, 4, 5. And it contains some actually like 1, 2, 2, 3, 3, 4, 4, 5, 5, 1. So that's one edge and X. Okay, then you have a hypergraph with edges. And what? Probability that the GNP is Hamilton is same as the, if you have this hypergraph, G ham, you choose a random subset. Random subset in a way that each vertex is included with the probability P. And it's a probability that this random subset contains an edge, is one of the edge. So these two are the same event. And here, so, I mean, that's kind of a setup that we want to work on. We consider hypergraph, and then we randomly select some subset. Then we see whether it contains an edge or not. Okay, and for this, I mean, we again only want to consider increasing property. So, meaning that I mean, if set X satisfies a property N, it's super that also satisfies the property. So in short, it's about whether it contains something or not. So if it contains something, it satisfies the property. That means if you add more vertices and it still contains it, so it's, I mean, it still satisfies the property. So super that will satisfy. Okay, to be more specific, I mean, to be more rigorous, the property is just the collection of subsets of the ground set. So we can say that some subset satisfy this property if it is in collection. Some subset might is not satisfying the property if it is not in the collection. But in this language, I mean, some set might satisfy property, but its superset might not satisfy the property. In such a case, I mean, talking about threshold might get weird, so we consider increasing property, where this is collection such that the collection say P, such that if X is in P and X is subset of Y, then Y is also in P. So that's the increasing property, like same with the monotone property we considered before. And with this setup, now, I mean, we consider it more general. We forget about the random graph or probability, more of like we consider a finite set X, which is the ground set, the universal set. And then let's say P is the number between 0 and 1. And we get the measure, use the P, is the product measure on 2 to the X, on the subset of X. given by this one is for each specific set, it included exactly this probability. I mean, that's a measure. So if you choose a p random set there, then what each set is included with your final set is exactly your chosen set is exactly F with the probability difference. And for an increasing family, say F, we write that the mu P of this F is the summation of all the member there. You add the probability of choosing them. And with this language, now we define threshold again in more abstract way. And we want to also define it in more, specific way. So before, the threshold could have many values. If it's threshold, 2 times it was threshold based on this definition. But let's give a unique number. So we define threshold, say P sub C over F for this, increasing property to be the unique P that satisfies is it exactly half. So meaning that if you randomly choose a subset, probability that that subset is in this family F with exactly. So for this, how do you obtain lower bound? We do just like before. So how did we find the lower bound for having K4? You consider the expected number of K4, and if that expectation is low, then they provide the lower bound, right? That P is actually lower bound. And if this is not K4, then you say the K4 plus 1, then you take a subgraph and then you consider all of them and then you compute the expected number of. And what does it respond in here? In here, what we can do if we consider a subcollection, say G, that's that following horse. So let's consider you consider all the elements there, then you add all the superset of this. You take union. And you can say that this is the set generated by this first. And if this totally contains F, then yeah, you consider such a, and then we say that such a collection is called cover of this. What's this F? What's this cover? For example, let's consider this this F0K. There, what's F? If F, if you consider all the subgraph of AN, where the H contains these, right? Technically, I mean, this is edge graph. So that's your definition of this increasing graph. Any graph that contains copy of this is F. Then, how did you find the expectation? I mean, first naive way was that you consider all copies of this F in here. And then for each copy, you compute the probability of each one if included in your random graph, and then you add them to get the expectation. So if you take this then what do you know? Everything here for every H here, you can find the one copy in this script G. That's subset of this. So in other words, if you generate everything here in this way, then all this F, this entirely contains all of this. Moreover, you can consider even copies of, say, K4 in this Kn, and again, this is a cover. Okay, and then what we do is that the following: if for all this cover, you just simply compute the probability, just like before. What did we add? For each copy of this K4, what we do? We compute the P to the 6. So this is 6 edge, P to the 6, and then we add for all the copies. So that's exactly N to the 4 times P to the 6 that we computed. We do the same thing. And if this is half, then what? You know that this holds, and this is exactly for all F you compute like this, and you take all the T, okay, which contains this F. For all that, you take a P. Basically, this is 1 that I'm gonna write. What? Out of this set, F of them are already fixed, and then left of them, we don't care whether they are included or not. We added for specific T, so for T minus S, it may be included or it may be not included. So we consider all the possibility. And this is actually 1, so these two are equal. And this is what? This is you take all T in F, and then you compute this one, which is like mu sub P of this F. And this inequality holds because this holds. So if we did for all of this, then that covers everything in F and maybe more. So that's exactly, what's doing here. It consider, every T in F are added at least once here. So you have this, that means your mu P is almost half. So that means your P is smaller than or equal to its threshold. So this provides a lower bound, and that this is exactly what we have done before by considering this expectation threshold in this random graph. And then here, you can consider different cover as well. This cover or this cover. And then whenever you have a cover, the P that you get from computing this X different, so you choose the back cover to get the better load. And we say that F is P small if there exists cover G with if, as I mentioned here, this will guarantee lower bound. And as this coincides with the expectation threshold in the random graph case, we use this to make the following definition of expectation threshold, or is more general set pattern. So Q of F is the expectation threshold of this increasing family F. F is the maximum P such that if F is P small. So out of all possible cover, you choose the best one and then see, what P you get with this equal to R. So you can get the lower bound on your threshold for each cover. Then you choose the cover that give you the best lower. And what would be the lower bound you get? That's your expectation threshold. And Kahn and Carlyle conjecture that this expectation threshold times log of the size of the largest edge in your hypergraph is an upper bound for the threshold. So let's say L of F is the maximum size of an edge in F or set in F. And let's say this F is L bounded. This hypergraph is L bounded if all the edges like the most. Then this Kahn-Carlyle conjecture is resolved by Park and Pham. The following, or that is constant, universal constant. AK. That's that. For every finite set F n non-trivial increasing property F, the threshold is almost k times the expectation threshold times the log of the largest size of the edge. Okay, so we will prove it in the next